Welcome to the deep dive. Today, we're looking into something pretty exciting, actually a new development in how we study gravitational waves. Yeah, it sounds like it could give us a much sharper view of some really violent stuff happening out there in the universe. So, our mission basically is to unpack this new technique. How does it work? Why is it such a big deal? And what does it really mean for understanding, well, the cosmos? We're basing this on a study published in Nature Astronomy. It's by researchers from Portsmouth, Southampton, and University College Dublin. And it really feels like one of those moments where, something seemingly technical deep in the weeds might actually unlock some pretty profound secrets about the universe. Okay, so maybe let's start with the basics, just to make sure we're all on the same page. What exactly are gravitational waves? I tend to think of them as like tiny ripples in space-time itself, like distortions when huge things like black holes smash together. Is that about right?
That's a great way to put it, subtle distortions, yeah. And they're produced by these incredibly energetic events, like black hole mergers, neutron-star collisions, and their importance. It's huge. I mean, the first detection back in 2015, that won a Nobel Prize. It really did open up a new frontier in astrophysics, as people say,
right,
because these waves give us info that traditional telescopes just can't get.
Because telescopes need light, right? And these events might not give off much light, or it's blocked.
Exactly. Or the event itself, like two black holes merging, doesn't really emit light in the way we normally think of it. So gravitational waves let us listen to these otherwise invisible events. It's a completely different sense for exploring the universe.
Listening versus seeing. I like that. But okay, if these signals are so faint and quick, how on earth do scientists figure out what they're hearing? What's the actual process?
Right. Well, it's quite a challenge.
Mm-hmm.
So when a wave passes Earth, our detectors, like LIGO and Virgo, they capture a brief signal. It's incredibly faint, it's just a tiny wiggle. And to understand where it came from, what merged, how big the objects were, how they were spinning, scientists have to do something pretty intense. They compare the observation against millions, literally millions, of possible theoretical gravitational wave signals generated with different models.
Millions. Okay, so it's like trying to match a fingerprint to a massive database.
Kind of like that, yeah. A huge library of possibilities. But here's the tricky part, and this is what the new research tackles. Dr. Charlie Hoy, who led the study, points out the challenge is that not all models are equally accurate.
Meaning the theoretical signals they're comparing against aren't all perfect.
Precisely. Calculating gravitational waves directly by solving Einstein's field equations, it's really hard, computationally speaking, extremely demanding. So many of the models scientists use have to make some simplifications, some degree of approximation. They're good, but they're not perfectly reflecting Einstein's theory in every single detail.
Okay, so they're like really good sketches rather than perfect photographs.
That's a decent analogy. And the standard way they analyze these signals is using something called Bayesian inference. Think of it as a mathematically rigorous way of weighing the evidence. You compare the data to the models, and it tells you which model parameters like mass and spin are most likely given the signal you detected. Often they'll run this analysis many times with different approximate models and then try to combine the results somehow.
Ah, okay. So if they're combining results from different models and some models are better than others, I think I see where the problem might come in.
You got it. The big issue with the older way of combining things is that it often can overlook how faithful each model is to Einstein's theory of general relativity. You might be mixing results from a really accurate model with results from a less accurate one without properly accounting for that difference in quality.
And the consequence of that is?
Well, the big danger is ending up with misleading conclusions. You might think you've measured the black hole's mass really precisely, but part of that measurement might be biased because of the approximations in the models you used. It's a subtle but really important effect. Getting this right, incorporating how accurate the models are, has been a known challenge. Dr. Hoy even mentioned, I've been thinking about how to incorporate model accuracy into gravitational wave Bayesian inference for years.
So it's been a persistent headache for the field. Okay, so what did this team do? How does their new method actually fix this? What's the secret sauce?
The breakthrough is how they handle that model uncertainty. Instead of running analyses with different models and combining them later, potentially ignoring the accuracy issue, their new technique essentially incorporates this uncertainty, the knowledge that models aren't perfect, directly into the Bayesian analysis itself.
Ah, so it's not an afterthought. It's built into the calculation from the start.
Exactly. It mathematically accounts for the fact that each model has its limitations, its degree of approximation, while it's doing the comparison with the real data.
Okay, that sounds like a fundamental improvement. So does this mean they've already discovered new things about black holes with this?
Not quite yet, in terms of brand new discoveries from existing data. The paper itself is more about proving the method. What it provides is a major improvement in the way gravitational wave data is compared to theoretical models. It's like building a much more reliable engine for future discoveries. It establishes that solid foundation.
Right, refining the tools before making the next big find. Makes sense.
And the immediate payoff, the crucial benefit, is that this improved method lets scientists obtain tighter constraints on the fundamental properties of black holes as a consequence.
Tighter constraints meaning more precise measurements.
Yes, more precise and, importantly, more reliable measurements. We can be more confident in the results.
And when we talk fundamental properties, what are we zeroing in on?
We're talking about key things like the mass and spin of black holes. How heavy are they? How fast are they rotating? These are crucial parameters for understanding how black holes form, how they evolve, how they interact with their environment. So getting these numbers right and knowing how right they are is fundamental.
So we're literally getting a sharper, more trustworthy picture of these cosmic giants. That's huge. It's like going from standard definition to HD for black hole properties.
That's a good way to think about it. And what's really smart about this new method is that it's designed for the future, too. As Dr. Hoy points out, gravitational wave models are continually being developed and will likely improve in accuracy over the coming years. People are always working on better approximations, better simulations.
So the technique isn't stuck with today's models.
Not at all. It's built so that once these newer, better models become available, they can be incorporated into our algorithm. It can adapt and get even better over time.
That's really forward thinking. It means the analysis itself can improve as the theoretical tools improve.
Precisely. The idea is that all models can then collectively help to obtain together constraints on the mass and spin of black holes. Even models with different strengths and weaknesses can contribute as long as their uncertainties are handled correctly. It leads to more robust science overall.
Wow. Okay, so this has been quite the deep dive. We've seen how this really clever new method isn't just a small tweak. It fundamentally sharpens our ability to, well, listen to these incredibly powerful cosmic events, turning faint signals into much more precise knowledge about black holes.
Absolutely. And it really underscores a key point in science, doesn't it? Sometimes the big leaps forward come from improving how we analyze the data, how we interpret it, not just from collecting more data or building bigger detectors. The analysis methods themselves are critical for extracting real understanding.
That's a great takeaway. And it leaves us with something to think about, doesn't it? For you, listening. If refining how we compare observations to theory can give us such a clearer view of something as mind-bogglingly distant and massive as colliding black holes, well, what other truths might be hiding in plain sight, maybe blurred by our current methods, whether it's out in the universe or maybe even closer to home? What insights are just waiting for us to figure out how to listen or how to look just that little bit more accurately? Makes you wonder.